Hello, today I will be just showing some examples of finding tangent lines for functions. Okay, let's go on to Desmos just to make things easier. So I just have a graph open. So let's say we have a function f of x. Make this lowercase f so it's easier to type. Let's say equals x to the power of 3. Now what a tangent line is. So the way you write a tangent, find the derivative of a function is just f, the name of the function, then apostrophe, and then an x. I didn't know this until a while back, but an alternative is doing d over dx. But this works for anything, so so it will work for any function that you put here. That's why this is also an option. Okay. So back to our derivatives and finding tangent lines. So what the derivative does is it finds the slope of the tangent line at x equals whatever that point is. So let me give an example. So if you know how to find the derivative, you should know that d over dx of x to the power of 3 is equal to 3 to the power of 2. 3 times x to the power of 2. Now what we can do is we can use this to find our tangent line. So let's say x equals 2. So let's plug in 2. And that means that x equals 2, this equals 12. But let's say we want to find the actual tangent line, so we need to know the whole formula. We need to plug in x equals 2 over here. So we do that. To the power of 3 equals 8. And now what we can do is we can use the point slope formula when you're given 1 point in the slope to write this out. Y minus 8 should equal 12 times x minus 12. No, x minus 8. There we go. Okay, if you don't know what point slope form is, it means y minus y1 equals m of x minus x1. If you're doing calculus, you should have heard of this already. This is just saying at xy, x1, y1, and then you have a slope m. M is your slope. This just gives you the function of a line at that point. So what we did here is that we just plugged in each of those values. So this is our y1, this is our m, this is our x1. And we can just plug in 8, 12, 2. What we can do as well, because we're on Desmos, we can just plot this as a point, and we have a drag and drop, drag around. Another fun thing you can do is, we don't need to call this m, we can actually use the derivative, because we know that m is equal to the derivative at that the slope of the line of that function at derivative. So let me try to access this point. Okay, so we got one thing. So what this is doing right now is it's taking the x value of the point, finding out the derivative of this function, plugging that the x value in, and it's using point slope form to create a line. But if we want to actually make this, what we also need to do is y1 cannot be y1 cannot just go around everywhere. This point needs to stay on the line, and we know that the y value should equal f of x. We don't need this. what we can just do is replace that with f of x1. This should be x1. Okay, and now what we have is basically a calculator for what the slope would look like in the tangent line. So let's go back to 2. So at that point, actually, I don't need to do that. I can just plug it in over here. So if you want to try to figure out what the slope is, we'll just use the slope formula. Okay, so at y equals at 1 equals -4, and at 2 equals 12. So then 1 minus 2. Oh, I did not, this is incorrect. That's the slope they were supposed to get. This is what we got. So this is x1, y1, y1 and x1. This is y2 and x2. I just found the slope. We can write this out as well. If you want to know the slope at that point, we just do f of x1. Now we just need to make this the derivative, and now we will always know what the slope is at that point. See, as we continue going, we can try again. Let's try at 1. So at 1, you apply power rule, so 3 times x to the power 2. So I wrote it up here. We plug in 1, the answer is 3. You notice our derivative is also saying 3. Now this doesn't just work for power functions, this works for everything. So let's do a trig function, sine of x. You notice we're still getting the tangent line at all of these points. The line is only ever making contact in this area once. It might touch the line more than once because of it just hitting other sections. I think one way we can fix that is we can restrict the range. 0 x 2 pi. I just wrote in. Okay, so it's still touching the line at other points, but you can see that that doesn't really matter for this because it's so far away. But if you keep on zooming closer, it's only ever making contact once. That proves that this is a tangent line. Now the tangent line for sine of x, the derivative of sine of x, is cosine of x. So you can just plug in derivative at, let's say, pi over 2. Pi over 2 is equal to -1. Our slope over here, I set this to pi over 2. Pi over 2. Our derivative, ooh, no, I wrote in pi over here. This should be pi over 2. You can see that it equals 0, and over here it also equals 0. So what I like to do, I just like to condense this all once again. If you have a function, f of x equals, we'll just write in something random here, 4x to the 5 minus 5x to the power of 3. And you want to be able to find the tangent line at any of these points. You need to know the derivative, and you need to know what your x value is. You need to know x, and you need to know the derivative of f of x. And all you need to do is just use point slope formula. This should be f of x. Your y value over here will always be f of x at that point. and this equals the derivative of the function, and you plug in your x at that point, and then you have the next part of your slope function, the x minus, and this should be x of 1. So what this is saying is you can just take any x value and it will give you a tangent line. I will post the link for this tool in the description. I hope you now understand how to find tangent lines, how derivatives come in handy when finding the tangent line of a function, and how basically how they are essential to finding it. I hope you now understand what point slope form is if you didn't know what it was before, and I'll see you later.